Here we go. Okay. So the exam on Tuesday will probably not cover the entire chapter 6. It'll be whatever we go through past Thursday. So whatever we finish with on Thursday, that's what we'll cover for the exam, and I'll make sure to be really clear on the objectives on Blackboard. Here's where we cut it off, so that you know what to focus on studying for the exam. All right, so we can review a little bit what we just did on the quiz. That was a good review, where we looked at the structure of neutral atoms. All the atoms in the periodic table, we did their electron counts, we did their protons, neutrons, all that stuff. Today, we're going to jump into chapter 6 and extend that to what happens when the protons and the electrons don't balance and we have a situation called ions. So if you notice, we're skipping chapter 5. Chapter 5 is nuclear chemistry. It's a whole different thing, and it would kind of not make sense to just jump into that right now and then go back to what we were talking about again before. So we're just going to do that later. So we're going to first talk about ions and kind of go on with the rest of the semester, and then we'll jump back to chapter 5 in a couple months. Today we're talking about ions. Ions are charged atoms. So instead of the neutral atoms we've been dealing with, these are atoms that have an overall electrical charge. So that means that the protons and the electrons do not balance. With neutral atoms, we always said we have the same number of electrons as protons. With ions now, we don't. We're going to have different numbers of electrons and protons. So let's look at how that works. Let's take a sodium atom. So a regular neutral sodium atom, we just write like that, just Na. How many protons does that have? 11, right. We find that from the periodic table. And how many electrons? 11, yeah. Because we always have to have equal numbers of protons and electrons in a neutral atom. So now we're going to look at something called an ion. A sodium ion would be written a little bit differently. It's still Na, it's still sodium. But now we put a little plus sign in the top right. And we say that that is a sodium ion. And what that little plus sign represents is that there's an extra positive charge going on. So this sodium, this Na plus, how many protons does it have? So if it's an extra plus, does that mean it has 12 protons? What do you think? Sure? Someone knows? Why now? Yeah, then it wouldn't be sodium anymore. If we're going to write Na, remember that the proton defines the name of the atom. So if we're going to call this thing sodium, it has to have 11 protons. If it has more, suddenly it's something else. So if it had 12 protons, it's now magnesium instead of sodium. So we have to stick with the 11 protons. So how can we make an overall positive charge if we're still sticking with 11 protons? What do we do instead? Yeah, we lower the electrons instead. So instead of 11 electrons, we have 10 electrons. So we still have an extra proton overall, but we still have 11 protons, so it can still be sodium. Everybody see how that works? Okay, let's try that with another one. We'll move down to calcium, down and to the right. This was on the quiz. So how many protons are in calcium? Protons? 20. And if it's a neutral atom, how many electrons?
20.
20, yep. Whoops, I should label that. 20 protons, 20 electrons. The most common ion of calcium is not calcium plus, it's calcium 2 plus, which means it's got 2 extra positives. And there's a couple different ways to write this. They're all okay. So if you prefer to call it +2, that's fine. If you prefer to just draw 2 pluses, that's okay too. Depending on where you're looking, you may see both of those somewhere. I always do it the first way 54, right. One more electron is going to give us that 1 minus. So that's how we make ions. Ions have more or fewer electrons than protons, but the key thing is don't change the protons. Whatever the identity of the element is, make sure that it stays the same number of protons. All right, so that's how ions work. Now there's a fun, okay, fun's probably an exaggeration. There's a trick to finding out what kind of ions we can form from different elements. And we call those common ions. So these are going to be the most commonly seen ions in the world. And we can figure that out by going back to our bucket model. So if we want to know a question like, what is the most common ion of, let's say, lithium, Li? What is the most common ion of lithium? We can figure that out by our electron counting. Here's how we do that. So we make our buckets. Our 2, 8, and 8 buckets. How many electrons do we have for lithium? 3, yeah. So we go 1, 2, 3. 1 valence electron and 2 core electrons. Now we need one more bit of information. Common ions usually have full or empty energy levels, or buckets. So those are our buckets, right? So if we want to know what the most common ion of lithium is, we can ask, how many electrons do we either add or take away to make full and empty buckets? And there's always 2 choices, because you can always either add electrons or you can take them away. So for the example of lithium, how many electrons would we have to take away to make full or empty buckets? Just 1, right? We take away that valence electron. Now the bottom bucket is filled and the other 2 are empty. So that's one choice. What's the other choice? What else could we do to fill our empty buckets? We could add 7. If we added 7, then we'd have 2, 8, and 0. Again, they'd be full or empty. They'd all either be full or empty. So what do you think happens? You think we're going to lose the 1 or gain the 7? I mean, I haven't told you how to decide this. I'm just curious if you have like a hunch about what it's going to be. You always go with whatever requires fewer electrons. So if you can lose 1, that's better than gaining 7. If you can gain 1, that's better than losing 7. So whichever one is the least amount of electrons to move around always wins. So we're going to say for lithium, we would lose this one. And if we lose 1 electron from lithium, what kind of a charge do we have for that ion? Positive how many? 1, right? We've lost 1 electron. So let's count it out and see. Our neutral lithium atom has 3 protons and 3 electrons. Before we even write it out, we're saying we're going to lose 1. So that's going to give us 3 protons and 2 electrons. And what does that look like? That looks like a +1 charge. It's got 1 more proton than electrons. Okay, let's try one on the other side of the periodic table. Let's try chlorine, Cl. See if you can do this one before I do. So do your buckets, or however you do that, however you do your energy levels. And then figure out how many electrons you have to either remove or add to end up with full or empty buckets. All right, so we did the buckets. You should have come up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So there's 7 out of 8 electrons in that last bucket. So what are you going to do to fill or empty the buckets? Add 1, right? And so what does that do to the charge? We go from a chlorine with 17 protons and 17 electrons to a chlorine with 17 protons and 18 electrons. So what does that charge look like? -1, right. We now have 1 more electron than protons. And so we've got an overall charge of -1. So this works great. It's a good technique, but it's a little bit time consuming. If we had to fill out this whole diagram every time we wanted to know the charge of an ion, it would take a while. And as we get more into the material, it would be kind of, we'd be spending our whole quiz time on one question. So we need some better ways to organize this. And luckily, the periodic table comes to our rescue here. Because remember that these charges that we figured out here are all based on the number of valence electrons. How many electrons are in that last bucket? And what does the periodic table tell us about the valence electrons? Look like you're about to say something profound. Yeah. Right. Yeah, exactly. So that entire column that chlorine is in is called 7A. All of the elements in that column have 7 valence electrons. So they're all going to get 1 more to get full levels and become ions. So they're all going to end up as -1 ions. So we don't have to figure this out for every single element all the time. We can just know that there are certain columns that are always going to have the same kinds of charges, and we can draw that and remember it. So let's draw kind of a outline of kind of a shitty periodic table, and then we'll put in some of these divisions and see where some of these go. So we just figured that out, that group 7A over here always seems to make -1 ions. What else can we generalize about on the periodic table? What other columns do you think we can figure out based on that idea? Yeah? Yeah, that lithium one, right? That was with one valence electron. Does everything else in that column also have one valence electron? It does. It does. So we can generalize for that whole column as well. And we can say all of these in 1A are always going to have +1 charges. In fact, pretty much, and I'll tell you some exceptions, but pretty much anywhere you can generalize about the number of valence electrons, you can also generalize about the most common charge. So where else would that be? Where else can we make some general rules about the number of valence electrons? It's being pretty quiet. You want to throw one out there? No, we don't know anymore? What about the one right next door? How many valence electrons in 2A? 2. So what's going to happen to those atoms? Are they going to want to gain 6 or lose 2? Lose 2. So 2A, those are going to lose 2 and become +2 ions. Yep. Yeah, what would you do if you have 4? So that's 4A. Any ideas? It is a problem. So that's one that we can't generalize about. Those species tend not to form predictable ions, so they can be +4, they can be -4, they can be +1 or 2. They can have some different stuff going on in there. So that's not one that we can write up here. But all the other ones we can. Now the other part of this is we have to be a little bit careful about where exactly we are in the periodic table. So like 6, we can go down the line here. So if 7A is -1 with 7 electrons, what do you think about 6A? Probably -2, right? Yep. I'm gonna run out of space here and think this through very well. And what about 5A? -3. And so this kind of works, but there's a problem, and the problem is that line, that metals, nonmetals stair-step thing. Because metals always have positive charges. So if we're generalizing -1, -2, -3, that doesn't apply to anything below that line. It doesn't really apply to the metalloids except for one of them. So we have to be a little bit careful about our generalizations there. So we can say that 5A is -3, but that only really goes for nitrogen and phosphorus and sometimes arsenic. And then number 4, we don't really generalize about. 3, boron is a little weird, so that doesn't quite work. The only other one that we can be generally sure of is aluminum right here. Aluminum is always +3. There are a few other scattered ones around the periodic table that always take the same charge. You don't have to memorize them. There's like zinc and silver and cadmium. You don't have to memorize those. But the ones that you can predict, we should know. And we can figure it out from the periodic table. So however you want to remember that, you can say negative charges are, how many spots are they from the right, and positive charges are how many spots are they from the left, or something like that. However you can remember that. And just remember that if you're in the middle of a test and everything goes blank, you can always go back to the buckets and figure it out, because that always works for the ones that we're talking about. All right, so what happens with that last column on the right, 8A? What kind of ions do they form? What do you think? How many electrons are in the valence shell for, let's say, neon? 8. So how many do we have to add or subtract to get to a full or empty shell? Are you shaking your head? None, right? Yeah, so those don't make ions. So we don't have to worry about that. They're happy the way they are. They're not going to add or subtract electrons. They're just going to stick with what they've got. So sometimes when an ion is formed, it's called the noble gas configuration, because it's like when oxygen gets 2 more electrons, it's kind of like it's jumping over 2 spots to be like neon. It's more, we could say it's happy or something. It's satisfied, it's stable. But those are some common ionic charges. So when we practice a little bit today with our last 15 minutes, we'll see how these work out, and it'll be a lot more convenient to use these rules rather than going back to the buckets each time. Okay, so keeping that sort of in our head for now, let's look at ionic compounds. A compound, remember, is made up of more than one element, more than one type of atom. So ionic compounds are going to be things like, are going to always be a cation and an anion, a positive charge and a negative charge. And the important thing, and the key to writing the correct formulas for these, is that we're going to always lead to a neutral charge overall. Now that's not true for everything ever, but for the stuff that we're going to deal with, we're going to have a neutral charge overall. So we take a positive charge thing, a negative charge thing, we put them together, and we make something neutral overall. That works, right? The only thing we have to do is make sure our ratios are correct so that there aren't any leftover positive or negative charges. So let me show you what that looks like. A common ionic compound would be the one made from a sodium ion and a chloride ion. If we put them together, we get NaCl, sodium chloride. Now notice that we don't write the little charges anymore when we're in the compound. That doesn't mean they aren't charged, it just means we don't write them that way because they balance each other out. So that's still a positive sodium ion and a negative chloride ion. They're just together now. And because it's +1 and -1, they're balancing each other out. All right, so that works. But what if instead instead of sodium chloride, we want calcium chloride? What's the common ion of calcium? What's the charge on it? Remember, think about where it is in the periodic table. +2, yeah. So calcium is +2. And chloride, we'll talk about that name, why it's chloride and not chlorine, on Thursday. But chloride is going to be same, -1. All right. So if we put those together in a compound, is it just going to be CaCl? That doesn't work. Why doesn't that work? Yeah. Right, it's not neutral overall. You've got +2 and -1. So if you made CaCl, there'd still be a +1 somewhere floating around there. So that doesn't work. So what you need is a second Cl. You need to change the ratio. Calcium and chloride can't be in a compound in a 1-to-1 ratio. They have to be in a 1-to-2 ratio. 1 calcium for 2 chloride. Because now we've got 2+ total, and we've got 2- total. So the way we express that in the formula is by making a little 2 down here, a little subscript 2, which you've probably seen in chemical formulas. And that shows that there has to be 2 chlorides for every 1 calcium. And that's how we balance the charges out. Let's try another one. We're going to look at a compound called sodium oxide. So that's going to be made up of sodium and oxygen. So now I want you to try this one. Figure out the common ion of each of them, and then what's the ratio they need to be in to make a neutral compound. All right, anybody figure that out? What? Not quite. Yeah, that's how it's going to be. So let's take a look at it together. What's the common ion of sodium? +1, right? What's oxygen? -2. All right, so how do we put those two together so that we have as much positive as we have negative? We need two of the +1s to balance out that -2. See that? 2 +1s and the 1 -2 make them equal. So the way we would write that compound is Na2O to show that we have 2 of the sodiums per the 1 oxide. All right, let's try another one. Aluminum sulphide. So this is going to be a compound of aluminum and sulfur. What's the common ion of aluminum? +3. That's the one from that column that we can reliably say is +3. And what's sulfide? -2, just like oxygen in that same column. So how do we put those two together?
We can add 1 S.
What?
We can
Add an extra S?
yeah, like -S.
Okay, so then we've got, does that match?
No.
Okay. It's okay, keep going. Yeah, so we actually have to kind of bounce back and forth. So now we've got too many aluminums, so we add another sulfur, and now all of a sudden they balance out. So you can keep kind of going back and forth until you get them to balance. Because now we've got 6 plus total, 2 of the 3 pluses, and 6 minus total, 3 of the 2 minuses. So that compound's going to be written Al2S3. And that's something that comes up now and then. So when you see that like a 2 and a 3, it's always going to be in that 2 to 3 ratio, like that. Okay. The last part of this is what to do about all those transition elements in the middle. So the transition elements have what we call variable charge. We've been just kind of ignoring them. But the reason for that is they don't fit any of our rules. So if we take iron, for instance, number 26, Fe, there's Fe plus 2 and there's Fe plus 3. If we take copper, there's copper plus 1 and copper plus 2. Some of them have even multiple different possible ions. So there's no way from just looking at the periodic table that you can tell what the charge is for any of those elements in the middle. You just can't, because there's different possible ones. So whenever we write the names of these ions and build compounds from them, we need to be very specific about which charge we're talking about, which ion we're talking about. So we can't say iron chloride change that. We can't say iron chloride because we can't know the charge on iron. There's just no way to figure it out. So instead, when a compound like this is written, the charge is given in parentheses right after the metal name. So instead of iron chloride, we might write iron, and for some reason it's always in Roman numerals. We would write iron 3 chloride. And that 3 tells us specifically that we are talking about iron 3 plus, or plus 3. That 3 tells us what the charge is. And it will always be there because otherwise we don't know the charge. So now we can do the rest of the problem just as we did, the rest of the formula just as we did before. We can say there's an iron 3 plus, there's a chloride minus 1. We know chloride is minus 1. And so in order to get those to balance, we're going to need 3 of these. So our compound is FeCl3. All right, try this one. What would be a formula for copper 2 oxide? We got it? What do you think? Kind of. That works, but you can reduce it, right? You want to have the smallest numbers as possible. Yeah. So so we can say that copper is plus 2 because of that 2 in the parentheses. We know oxide is minus 2. So our compound is 2 plus 2 minus. It works out just like that. So CuO. Yeah, Cu2O2 also works, but usually we do formulas in the lowest possible numbers. So if we can reduce that to CuO, that works. This example shows something that's a really common mistake in doing these things, which is a lot of people want that thing in parentheses to be the subscript or to have something to do with the subscript. And it doesn't. It's the charge. So we call that compound copper 2 oxide. And that makes your brain think that it should be Cu2O, but it's not. because the number is the charge, not the subscript. And the reason for that is because copper 2 oxide, copper 2 chloride, copper 2 nitride, whatever, those are all different compounds with the same ion. So that's still a copper 2 ion. All right, so remember that number, and we'll keep reminding you of that, but that number corresponds to the charge, not the subscript number. Okay, so that's how to build ions and make ionic compounds. Now, on Thursday, we're going to talk about how to go the other direction, which is how to come up with names for ionic compounds given the formula. And that's a little bit tricky too. So if you want to get a head start on that, look at those rules in your book. You can also watch the video from my class last night that's on YouTube. That'll kind of catch you up and at least give you a little head start into what we're doing on Thursday, because that stuff will be on the exam on Tuesday. So if you want a little extra time to look at it, I would suggest you do that between now and then. All right, so take about 15 minutes, get your pre-labs finished up or whatever, and then we'll get started at 2 for lab today.